Raja. Thank you so much for having me here today, and I'm really excited to talk to you a little bit about your background and your interest in astronomy. But first I thought we'd talk about the big astronomy event of the year, the solar eclipse. And I was wondering if you could tell me a little bit about your experience seeing the eclipse, because I know you got to see the total eclipse.
Yeah, it was quite amazing. I'd never seen a total eclipse before. I'd seen a couple of close shaves, so 97 and 95, but it's the difference between that and totality is, as they say, night and day. It was really, really quite remarkable. The fact that you could take off your glasses during totality and look at the thing directly was amazing. And I'd been told that in addition to my own experience, me and the sun and moon, in addition to that what would be amazing would be the reaction of everything else around, the people around me and the animals and even the plants, and that lived up to it, So people were just going crazy all around. People were going crazy. Dogs were going crazy. The birds were going crazy. I didn't see this, but some of our friends were saying the daffodils sort of shut down temporarily and then opened up again. It was absolutely amazing. And what was striking was how big the stuff associated with the sun is compared to what my impression of the sun was. There's this corona that's 5 times bigger than the sun that you could see, and it's nothing like a symmetric thing. It's just all over the place. It's a complete mess. It looks like a train wreck out there. It's just quite amazing.
Really cool. So backing up a little bit, can you tell me a little bit about where you grew up and your background and when you first became interested in science?
Sure. In fact, there's a nice eclipse connection there because I was talking about the close shaves. There was a 1980 eclipse that was it was a total eclipse a little further south in India, further south of where I grew up. I grew up in the big city of Calcutta, where you're lucky if you got to see the sun at all. There's so much air pollution, and you certainly couldn't see any stars. There's so much light pollution. So the sun was the only bit of astronomy I got to see directly by eye. And so there was this 97% eclipse I still remember, 16th of February 1980. And it was total a bit further south in, the path of totality went through points in India further south. But at that point, I knew no better. I said, wow, 97%, that's really cool. I had no idea that, that remaining 3% is everything. If I had gone to see the total eclipse, I would have seen many more by now. I'm sure I would have chased them. But I grew up in a big city with where you're not immediately attracted to astronomy, unlike say growing up in Los Altos or growing up in the desert, where all you have to do is go out and look up and see the stars. So my interest in astronomy, I think, came from a visit to a planetarium. So we had an amazing planetarium which still exists. There's an amazing planetarium, all analog projector. So this is a monster of a projector that I don't know, taller than a human being, and just with many lenses and mirrors and lights, and each one had its little task of projecting something onto the planetarium dome, and it would move across, all analog. And of course, modern planetarium projectors are not at all like that. It's all about what database you have, and the projection system is very simple. But I was probably more fascinated with the projector than what it was projecting, but it still got me hooked into astronomy somehow.
How old were you, do you think, when you first really developed an
I don't know,
interest?
and that's a good question, and I don't quite know. I think I was in elementary school, I think. The planetarium was not a one-time visit. We would go there often, and that's why it's hard for me to know when I got bitten by the bug. I didn't notice when I'd been bitten by this bug, by the astronomy bug. So it was a latent carrier of the astronomy bug for many years, and it sort of took a while before I let it sort of take over my conscious thinking. And so I think I was in college when I was conscious of this love of astronomy. I would go over to the library and borrow books about different, whatever I could lay my hands on. And I'm surprised I became an astronomer because one of the first books I laid my hands on was very technical and was about the interiors of stars and how they shine. It was all about radiative transfer and hydrodynamics and thermodynamics. And It was awful. It was a tough book. I later met the author, and I told her that the book had actually plummeted me into astronomy. I didn't tell her it was in spite of how technical the book was. It was, but I went to a lovely Christmas dinner at her place in the UK many years later. But that one book I remember because I was so lost. I had, it's one of these moments where you think a subject is what it is, and or you have some vague ideas about what a subject is, and you read one book and it completely throws you off and says, oh my, it's nothing like this, And neither extreme was right. That book was very technical, it was a very specific thing. That's not the thing you and I work on now. That I think was, those were important elements in my, taking the plunge. There were other books I read that were more accessible. It's a book by a very famous cosmologist, a steady-state cosmologist, something most astronomers don't believe anymore. But he wrote a wonderful book about Big Bang cosmology and the physical universe. A guy named Jayant Narlikar wrote a lovely book about that. And then there's a wonderful Weinberg book, Stephen Weinberg, the Nobel Prize winner. He got this is the weak nuclear force Nobel Prize, the electroweak unification Nobel Prize winner, who wrote a book called The First 3 Minutes. It's like a little movie. It's a frame-by-frame description of the early universe, and with just the right amount of physics for me at the time, and it just worked out beautifully. That book did what the other books hadn't, which is it gave a nice combination of technical detail and big picture, and said, "Wow, this is fun. This is what I want to do." There were. This was all happening in college. It was all happening on the side. I mean, I had a busy academic track that had no astronomy in it, sadly.
So it was just physics that you were primarily
It was just
studying?
physics, some chemistry, some math. So the college structure is such that you essentially do a major and 2 minors. Everyone does. So you pick your major and you do 2 minors. My minors were chemistry and math. They're not called minors, but it's effectively that.
So for you, was the taking the plunge, was that applying to graduate school?
It was applying to graduate school. It was really making the decision in my mind that this is what I want to do in grad school. I would have applied to grad school anyway in physics, but it directed what I applied to, how I directed my application. I applied to astronomy departments or departments that had astronomy as part of a physics department, or ended up going to an astronomy-only department. So it did direct it focused my applications for grad school. It also focused what I did to foster my interest outside of formal education. So I took it upon myself to learn tensor calculus, and that was the hardest thing I've ever done. I took it upon myself to learn general relativity, the math of general relativity, because people warned me that when you go to grad school, they're going to assume you've taken this as an undergraduate. And sure enough, that's exactly what happened. I went to grad school, and my professors and my fellow students, my fellow students already had done this. My professors assumed we'd all done this, so I'm really glad I had sort of self-taught GR and tensor calculus to fall back on. So it's those sorts of things that was the plunge in some sense.
So you decided from some reading that you were really interested in astronomy. What was it like when you actually arrived at Princeton for graduate school and you were all of a sudden in a research environment? What was that transition like? Scary
as heck. It was as though everyone else had this manual that they'd been reading for the last 10 years, and they knew exactly what to do, and I still didn't have the manual. I had no idea what to do. It was scary and energizing at the same time. It was scary because of how much my fellow students knew. So I had 3 classmates. One was from the University of Toronto, an undergraduate. One was from Yale, and one was from UCSD. And each of them had done undergraduate degrees with a significant amount of astronomy in their curriculum. They were light years ahead of me in the following 3 ways: in terms of their content knowledge of astronomy, in terms of their technical knowledge, meaning they knew how to program a computer, whereas I hadn't seen one, I had read books, but I'd never seen one. I didn't know what a username and password were, those kinds of things, those minor details. But they were completely conversant with all this. And the third way in which I was light years behind them was they had a very clear sense of what research entailed. They were used to reading about other people's research. They'd done some research of their own. They'd published, or they'd come close to publishing as undergraduates. So those three were both my biggest source of an inferiority complex, but they were also my best resources for learning. So I say it was scary, it was downright demoralizing, but at the same time, I remember when I went to bed every night, I would make a mental list of all the things I had learned that day. It was a very long list every day. It was a very long list every day. And so, but that list just gave me strength, because it said, these are the things I didn't know at the beginning of the day, and these are the things that I'll wake up knowing tomorrow morning. And much of that was learned from my classmates. Some of it was learned from my professors. But it was very scary to walk into that class, because our classes, were taught by Jerry Oestreicher and Jim Gunn. It was a class on galaxies, and it was entirely a class on. During the meetings, we would discuss papers that assigned us to read, and they gave us an insane amount of reading. And looking back, well, not just looking back, even then we knew it was an insane amount. If we did nothing else between meetings, that's all we would be doing, is reading those papers. And of course, we had plenty of other things to do. And our class meetings were entirely discussion of what papers people had written, and so it was a very different way of learning compared to what I'd been used to. There was very little emphasis on textbooks, which is all I had known before. Textbooks and blackboard equations are all I knew before, and in terms of learning and teaching styles. So the teaching style was also a huge shock. I'm amazed I survived it. Thinking back, I'm just amazed that I survived it. And I think I survived it because I had taken the plunge. I said, I'm going to do this. It doesn't matter what. I'm going to adopt whatever comes. I'm going to make it work.
So you made it. You survived your PhD, and then you stuck with it, and are now a professor. So you must enjoy doing research. What do you enjoy about what you do?
Two things. I'll give you the less important thing first.
Okay.
So the second most important thing in my research are the questions themselves, the curiosity, the size of the questions themselves. They're huge questions. What is the universe made of? How is it going to end? How did it start? This is a big question. There some of just in terms of sheer physical size, in terms of the time scales, in terms of the dynamic range of energies, temperatures, densities. I can't think of bigger questions. I don't think anyone can think of bigger questions. You can think of bigger questions possibly that are philosophical, but I can't think of bigger scientific questions. Quite literally, they're very big questions. So I feel fortunate, and I enjoy the fact that I get to tackle even a small part of some of these huge questions about ourselves, about humanity, about life on Earth, about our planet, about our star, about our galaxy. Galaxy part is what I care most about, as do you. So the enormity, the attractiveness of the questions, the fact that they're even that one can make a dent into some of these questions, one can tackle some small part of these questions is remarkable, given how small we are compared to the subject of these questions. That's exciting. That's exciting. You know this. You sit on a plane, you tell someone you're an astronomer, you can kiss the next 5 hours goodbye. You have a set of questions from if the person's interested. It's clearly I feel fortunate that I can that I get paid to do this stuff. And when I talk to people, when you talk to people, I'm sure you get the same thing. Wow, you get paid to do this stuff. It's fun. That's the second most important thing. I would say the first and most important thing, and I can say this now looking back, it's been the people. It's been the people. It's people like you. It's people like my other students. It's my mentors, my teachers, and people who are outside that. That's my scientific family, my students, and the people who saw me as their advisees, as their students. That's the inner circle, if you like. But outside that inner circle, there are people I've come across whose experiences, whose thinking have been amazingly inspiring. So I always feel the people part of the journey has been the most fun. And as I was saying, I got to meet Eva Novotny, the author of that stellar structure book. It was so exciting it was so much more fun talking to her than reading her book. And just that, just that aspect of it, talking to, getting to know Martin Schwarzschild, who had some contact with Einstein, or the professor at my college whose book I used to learn tensor calculus. His advisor was a collaborator of Einstein. And just seeing that these people are no longer, just getting the sense that these people are not in the ivory towers you imagine, that that people who knew them, or you knew people who knew them. So seeing that the number of degrees of separation is small, can be counted on the fingers of one hand. That's been the most exciting thing.
So this is a nice transition into the more technical section of the STEMcast. And so you've alluded a couple times to the fact that both you and I are very interested in galaxies. Yeah. So can you tell me what you are passionate about with galaxies? Why are you fascinated by galaxies?
So a galaxy, at the face of it, on the face of it, a galaxy is a collection of stars. And we live in the Milky Way galaxy, and we can look up in the sky and see this band of light that is our collection of stars, our sort of galactic level home. But it's more than just a collection of stars. It's a collection of the raw material that can make new stars. It's got gas and dust in it that not all galaxies do, but many do, most do. And even more importantly, galaxies have this stuff that holds all of this together, this invisible stuff that holds it all together, this so-called dark matter, whose gravity is doing the task of keeping us one family, keeping us, one family of stars, gas and dust. Even though we can't see the dark matter, it's performing an extremely valuable function. Its gravity is the dark matter gravity is the dominant source of gravity on the scale of galaxies, on the scale of most galaxies we know. That's actually what separates just a simple collection of stars from a galaxy. A galaxy is not just a collection of stars, it's a collection of stars and the dark matter that holds these things together. So that's, if I turn this around, this is a reason why galaxies are important. You can study the importance of dark matter, the amount of dark matter, its distribution, its assembly process on galactic scales by studying galaxies. And you're studying this part of your PhD thesis, the assembly history of dark matter in the Milky Way and the total amount of dark matter in the Milky Way. Those are important things to understand. Galaxies, therefore, offer us a visible, not audible, but a visible channel to understand how dark matter is assembled on these scales, on galactic scales. On smaller scales, on the scales of stars and planets, dark matter is very difficult to study. And stars are not dependent on dark matter for how they shine. They're dependent on the gravity of ordinary matter. Same for planets. Planets are responsible. Planets are held together by, planets have collapsed under their own gravity. They're also orbiting stars because of the star's gravity. There's no dark matter needed or to make that work. There is no dark matter. There's no importance of dark matter on these smaller scales. So galaxies, I see that as the first scale on which dark matter can be studied in a meaningful way. You can study dark matter on larger scales, on the scale of collections of galaxies, and people do that. You could study dark matter on the scale of the universe itself, and people do that. But below galaxy scales, on smaller than galaxy scales, you really have to get down to the particle level of dark matter or the clumping level of dark matter. The Macho project, which is looking for lumps of dark matter, or the projects that are searching for WIMPs, the weakly interacting massive particles that could be dark matter. That's a very different kind. These are very different ways of searching for dark matter. I like searching for or understanding dark matter on galactic scale. So that's why galaxies are important. So the chemical enrichment history of galaxies and dark matter are two things that you and I, they're actually both part of your thesis, and there's certainly big elements in most of my research. Not all of it, but most of it.
So you also have done extensive work on the Andromeda galaxy. So why might someone study the Andromeda galaxy?
The Andromeda galaxy is important because because we're outside it. Heck, it's like it's a combination. Well, the Andromeda galaxy is important because we don't have a big enough selfie stick, to take a picture of our own galaxy from the outside. So
that would be an awesome thing to have.
So it's a way of us looking. It's a vicarious way of looking at our Milky Way from the outside. We think the Andromeda galaxy is like the Milky Way, but we're both outside it, but close enough to it that we can see a lot of detail. So it's many analogies have been made. One of them is like looking out of your window at your neighbor's house and trying to understand what your house might look like from the outside, or trying to understand what your house might look like if you had the ability to walk through your house, which we don't in the Milky Way.
Right.
We can't walk through our own house. Just haven't had it's too big. But we have our neighbor's house. We have many neighbors, and this particular neighbor, the Andromeda galaxy, happens to be similar to, slightly bigger than our own, and it's the closest neighbor that's bigger than our own. So it's become it's become a big part of my research, and taking those images for the first time of the Andromeda galaxy, I'd never been an amateur astronomer, but I felt the same kind of thrill that an amateur astronomer feels. You're taking your own picture, saying, "Wow, this is what this galaxy looks like. And it's my picture. It's my digital image of the Andromeda galaxy." That was no small part of the thrill and the business of getting hooked into studying galaxies. We've talked about getting hooked into becoming an astronomer. There were many levels of falling in love, and falling in love with astronomy came first, but then falling in love with galaxies came later, and I think a lot of that had to do with just taking my own pictures at one stage on a cold night in outside Tucson, taking these pictures. Miserably cold night. We were listening to the election results, and this was the first Bill Clinton election, and my collaborator Shomuk and I were taking these pictures of the Andromeda galaxy. It was just it's one of those things that there was something visceral about those this beautiful image of a galaxy.
Yeah, I understand. My first observing trip, I took images of the Orion Nebula, and it was just magical, honestly, and made it into a color image, and I still feel so proud of that, and that was my picture. And
Where were you when you were doing this?
at Kitt Peak.
Oh, okay, same place.
Oh, you were at Kitt Peak too?
Yeah, I was at Kitt Peak. I was at the Burrell-Schmidt telescope, probably a different telescope.
Yeah, I was on the 0.9 meter wind telescope.
I see, okay. This is the Wisconsin, Indiana, Yale.
Something like that.
The NOAO telescope, yeah. No, I was at the same mountaintop, different time, decades ago. So this was
different time. Yeah. I think I was quite young when you were taking those.
No, it was. I don't think. Well, we won't go into this, but I think it was. I took these pictures in 1991, 92.
So I would have been an infant. Yeah.
Oh, good. Okay.
So you mentioned looking at these pictures that you'd taken at Kitt Peak of the Andromeda galaxy. Nowadays, what are you doing to study, or what is the community doing to study Andromeda?
We have fancier toys now, right? So the Kitt Peak telescope was the particular telescope we used was a very small telescope. It was a 0.6 meter telescope. So the diameter of the mirror was 0.6 meters, and it had a relatively simple camera behind it. A single CCD, etc. So the toys have gotten way more sophisticated. To be fair, there were already more sophisticated toys around, even when we were taking those pictures. So I'm particularly excited about two flavors of toys, two flavors of instruments and telescopes that we've trained on the Andromeda galaxy, and both of which are a big part of your research at UC Santa Cruz. One of them is the Hubble Space Telescope, The other is the Keck telescope.
The nearest galaxy to our Milky Way can be found in the autumn constellation of Andromeda and is located 2.5 million light-years away. NASA's Hubble Space Telescope has photographed a portion of this galaxy in never-before-seen detail. Hubble's sharp vision can resolve over 100 million individual stars in the Andromeda galaxy. Large groups of young blue stars indicate the locations of star clusters and star-forming regions. These clusters are interspersed among a smooth distribution of cooler red stars and lanes of dark dust.
So one interesting measurement that was made using data from the Hubble Space Telescope is the motion of Andromeda from side to side. Right. And we know the motion of Andromeda coming towards us, and it was found that Andromeda galaxy is heading straight for us in the Milky Way. So I was wondering if you could sort of tell us a little bit about what planet Earth and our sun is in for over the next several billion years.
No, that's an excellent question, an excellent point you raised. There's good news and there's bad news. The bad news, as you said, is we're heading for a collision. The Andromeda galaxy is coming. The bad news is there's no place to run. There's really no place to hide. The good news is there's a lot of time. It's going to get here in 5 billion years. We have plenty of time to figure this out. Bad news is there's nothing to figure out. There's really nothing to do. Absolutely no place to go. The good news is nothing bad is going to happen. So the solar system and the connection, the gravitational connection of our planets to the sun is not going to be affected by this collision. There's a vanishingly small probability of that bond being broken. The bond that can be broken is the bond of our solar system with the Milky Way galaxy. The entire solar system is in orbit around the center of the Milky Way, and that bond is more fragile. During a galactic collision, that bond could be broken. We could become orphans as opposed to a member of a galaxy. We as a human species call the Milky Way galaxy our own because our solar system and the sun is in an orbit around the center of the Milky Way. That bond could be broken. Not a catastrophic bond to be broken, because it's not like life on Earth depends on the collective light of stars in the Milky Way, not at all. Mm-hmm. It's okay for it to happen now. If it had happened a long time ago, before the chemical evolution of the sun had happened, before the sun had been born, if it had happened to the nebula from which the sun formed, if we had been orphaned from our galaxy, that could have affected our chemistry, could have affected how complicated or simple the periodic table is that chemistry students on Earth study. Mm-hmm. Chemistry could have been a very easy subject if we had been orphaned before the sun was born. It would have two elements. It would have hydrogen and helium, and life would be simple. Chemistry would be there would be no AP chemistry at all.
Okay. So to sort of wrap things up, I wanted to ask you a couple questions about the Science Internship Program, SIP, of which you are co-founder. You mentioned in your background that you didn't really do any research until you arrived at graduate school, mm-hmm. and now you support dozens of high school students every summer doing research at UC Santa Cruz. Can you explain why you think it's important and valuable that high school students get involved in scientific research?
I see the struggles I had because of the fact that I didn't have any exposure to research at high school age or even college going age. I see the struggles. Looking back, it's very easy to see those struggles. I probably couldn't see it as clearly when I was going through the struggles at the time. But with the benefit of hindsight, I can see how disadvantaged I was because of my lack of exposure to the research style of thinking, to tackling open-ended questions, to tackling problems where your advisor or mentor doesn't know the recipe for the answer. So I feel I feel it's important to get that exposure at an early stage. There's nothing magical about high school. There's no reason why a student couldn't get exposure to that even earlier in middle school or elementary school. And honestly, that does happen in the best educational settings. That does happen. Very young children get a sense of problem solving in this sort of open-ended setting. So looking back, so this one way of looking back is to say, look at my own experience. I didn't have this, but I can see how beneficial it would have been to have this. So can I give this? Can I make this happen for other students whose experience can be very different from mine? But it's all fine for me to say this, but it's not like I came up with this idea. I completely stumbled on the notion of engaging high school students in research. I would be misleading you if I said that it was all planned. I didn't have this experience, and I thought it would be great for high school students to have this experience. No, it wasn't at all like that. Someone else thought it would be a good idea, and I just happened to go along with it, with the experiment. So. There were teachers and schools there was a particular teacher in a particular school who felt that her students were really strong and that they were mature enough to take on open-ended research questions. They didn't have access to what the important questions were or the data sets and techniques needed to tackle those questions. And so the teacher approached me to say, would you be willing to supervise them through this process? And it was, I had no idea whether something like that would work. So when I took it on, it was an experiment. I knew it wasn't, doing that experiment wasn't based on personal experience. It was the opposite, because I knew that as a high school student, I would have had no idea what to do. So I took this on thinking, yeah, sure, let's give this a try. And, something, it started with something small, but it's grown into something much bigger. It started with just a few students trying this. Now there are hundreds of students who've gone through this program who've done open-ended problem solving in a particular subject. Each student has worked on a particular subject, but now there's a wide range of subjects that the program has offered to students. Over a dozen subjects across the UCSC campus. Now, it's had all kinds of. We were talking earlier about contextualizing one's work. You've asked me to contextualize my work in the context of why our galaxy is important, why are, and I said it was because of chemical evolution and dark matter. I can say this now after having been a researcher on galaxies for 30 years. When I was doing the research itself for the first time, I had a very hard time contextualizing it.
Sure.
And I think any first-time researcher it gets so deeply entrenched in their work that it's very hard to step out and see why this is important. And that's but it's important to be able to step out and put it in perspective. And that's not a small part of what we are trying to get young people to appreciate. Not just the technical detail, but how it fits into the bigger picture, and balancing those things. Digging deep into a trench, but also taking the time to come out of your trench, climb a hill, see the whole battlefield, and see how your trench is contributing to the overall battle. Balancing those things. The latter of seeing how your trench fits into the bigger battlefield is, in a way, a harder thing to teach, harder thing for a young person to appreciate than just the digging. You can put your blinders on and dig. Yes, it takes strength, it takes courage, it takes persistence, but it takes vision to understand where your trench fits into the battlefield. And that's a harder thing to learn, teach, appreciate. So I think those have been the key take-homes for the high school students in this program. But the human interaction that we were talking about earlier, the people, the close mentoring, the mentors serving as role models, their journeys seen through the eyes of a young person who's about to embark on a journey, that's been an important part of the whole thing also, the people part of it.
So you mentioned a few qualities, courage, persistence, and you've supervised, I think I'm your 13th PhD student. Is that, I'm number 13? I think I'm number 13.
You're number 13? Lucky 13.
I think I'm lucky 13. And unless I'm 12. I'm going to say I'm lucky 13.
All right, you're lucky.
And you've supervised, you've seen hundreds of students at this point go through SIP. What do you think what are the qualities that one should work on in oneself to become a successful scientist? What are the most important qualities of being a scientist?
I think persistence is a really important quality. It's like the very nature of research is, you don't succeed. You fail many more times than you succeed. So having the maturity, the confidence, the faith that you're failing because the problem at hand is difficult. It's not you, it's the problem that's causing you to fail so many times. That's part of persistence. But that has to be balanced with understanding when you really hit a brick wall and you need to change direction. So, so I think persistence is really important. Being passionate about why you're doing this. It's very hard to understand why you're passionate about something, but try to articulate that even in one's own head, not to someone else, just to yourself. Understanding why you're passionate about a particular subject is really important, because that will get you through the struggles. That will get you through the path that requires your persistence. So I think passion and persistence, those two P's, are probably would be at the top of my list of what it takes to to succeed in any technical field. And I think in any field, why technical?
So do you have any advice for younger students, high school students, perhaps who are interested in going into STEM? Any pointers for them?
I would say that for young people who are looking for careers in STEM, they shouldn't limit themselves to any particular narrow area too early in the game. STEM is very, the different aspects of STEM are very interconnected, and many of the subjects you study in high school are siloed in ways that are not realistic in the context of how STEM is used in the real world. So it's important not to fall to avoid those pitfalls of thinking that I'm interested in biology, I'm not interested in chemistry or physics or math. These subjects are so connected in the real world. So avoiding getting siloed into one particular thing like that is really important. Really listening to your heart, understanding what your passion is. Your passion, not your parents' passion, not your teacher's passion, not your peers, it's your passion. Taking ownership of why you are interested in something is important. And too often, kids are pressured into going a direction that their peers are interested in or their parents are interested in. I was fortunate to have parents who didn't push me in any particular direction. I didn't follow either of their paths. But I was fortunate to have that support, and not all kids have that. So a lot of kids feel pressured, pushed by people around them. So avoiding that, having the strength to at least understand and articulate your own passion would be a bit of advice I have. Looking for your support network, the mentors you talked about, finding mentors whose style of thinking, whose style of working meshes well with your own. It's an important thing for a high school student to understand. I'll give you one more thing, and I think this is something that's often ignored in STEM. Communication. Articulating your thoughts, organizing your thoughts within yourself, communicating well with others, is such an important part of everything we do in life, and it's something that is often it's often given the short shrift in STEM. So you don't need to writing and technical writing is technical writing, but no, technical writing is, there's a lot of creativity that goes into writing. There's a lot of organized thinking that goes into writing. These are quote unquote soft skills that are exceedingly important. They're not soft, in my opinion. They're at the core of what makes someone a successful scientist or a successful person.
Great. Well, Raja, thank you so much. I really enjoyed our conversation.
Thank you. Thanks for taking the time. Those were great questions.
Oh, thanks.